Good evening, my dear students. Good evening, all of you. Good evening, my dear students. Good evening, all of you. My name is Lakshmanana. This is Ellen Brand of Chemistry. Today we are going to discuss about 13th group elements. So 13th group elements are also called as boron family, right? So 13th group elements are also called as boron family, right? So boron family, what will be there? What are the elements are there? So boron, aluminium, gallium, indium, then thallium. Boron, aluminium, gallium, indium, thallium. Sir, here atomic numbers, in case if you write, the atomic number of boron is 5. Then magic numbers, well, writing the atomic numbers of all these elements, you have to remember magic numbers of 13th group elements or P block elements totally. So we call it as magic numbers if you take. So what are the magic numbers will be there here? So 8, then 18, 18, 32. These are the magic numbers. Then atomic number 8, if you add 8, so atomic number 5 is there, 5 if you add 8, then aluminum atomic number you can get that in 13 atomic number. So now, so in case gallium, so 13 if you add 18, so atomic number for the gallium is 31 you can get. Then next again 18 if you add, so that is 31 and then 18, then 49. Atomic number for the indium is 49 you can get. Then thallium, so 49 plus 32 if you add, 32. So 9 plus 2, 11, then 4, 18, 8. Then atomic number for this is 81. So these are the 13th group elements, or we call it as a boron family. So boron family atomic number of these, right, my dear students, understand all of you. The electronic configuration of boron, if you take, then 1s2, then 2s2, then 2p1. So 5 electrons are present in it. So 2s2, 2p1. So 2s2, 2p1. The valency cell of electrons, 2 plus 1. How many electrons are there? 3 electrons. So valency cell in the 13th group, only 3 electrons are there. So if you take aluminium, you can get it is 3s2, 3p1. Then here 4s2, 4p1. Then here 5s2, 5p1. Then here 6s2, 6p1. 6s2, 6p1. Clear, my dear students? Understand all of you? Right? So all these elements in their valency cell, it can get 3 electrons, 3 electrons, 3 electrons, 3 electrons. So valency electrons, look at valency electrons for the 13th group elements are 3. Valency electrons for the 13th group elements are 3, and also tell that is oxidation state of 13th group elements. So oxidation state of 13th group elements are +3. Common oxidation state of 13th group elements are +3. That you have to remember. So one by one we have to discuss about in this. So first we have to discuss about the boron, main important element in it. So boron family, boron we have to discuss. What is the boron? What characteristics are there? That we have to discuss about the boron. So first if you take boron, it is one of the hard substance. Boron is hard substance. It is present in the black colored crystalline substance. Black colored crystalline substance. It is crystalline substance. Then remember, it contains icosahedron structure. Icosahedron structure. So which is boron. Then remember boron, it is very hard material. High melting point is present. High melting point is present for the boron. So boron actually, it's a boron. Sir, isotopes in case if you take isotopes of boron, if you take isotopes of boron, if you take isotopes, nothing but isotopes, same atomic number, different mass number of the elements are called isotopes. Everyone knows, right? Yes. Then boron isotopes, two elements are there. One is atomic mass with 10. Atomic numbers of borons both are 5. The atomic masses, one is 10, one is 11. Then boron 10 atomic mass, it is contains 19 percentage. This contains 81 percentage in the natural abundance. Remember, my dear students, isotopes 10, 19 percentage, 11, 81 percentage, 11, 81 percentage. Then, so look, my dear student, here, so one more important, that is boron 510. So boron 510, 19th percentage it is. So it is used in nuclear reactor, nuclear nuclear reactors. It is used in the nuclear reactors. So why? Because it can absorb the neutrons. It can absorb neutrons. It can absorb, ability to absorb neutrons. So this is about the boron. Remember, it is a very hard substance. It's a black colored crystalline substance. Icosahedron structure is present. Boron isotopes 10, 11 is present. Then high melting point is present for the boron due to the strong solid. Then say here boron 19. So 19 percentage of that is isotope of this. It is used in the nuclear reactors. Why it is used in the nuclear reactors? Because it can absorb neutrons. It absorbs neutrons. Okay, my dear students. Next, very important, we have to discuss about so trends which are present in it. What are the trends? So what are the trends? Periodic trends we have to discuss. So what are the periodic trends that we have to discuss here, my dear students? Look at carefully. So yes. So if you take periodic trends, yes, sorry for the inconvenience. So I got a call when we are doing the class. Sorry for the inconvenience. Yes, come to the point, all of you. So we are discussing periodic trends. Periodic trends. So periodic trends, nothing but what are the periodic trends, sir? The periodic trends, nothing but one is atomic radius, electronegativity, density, then boiling point, melting point, then all these that we have to discuss. All these we have to discuss. Clear? Okay. Right. So next, look at the periodic trends. So look at the periodic trends that are first, so boron, aluminum, then gallium, then indium, then thallium if you take. Boron, aluminum, gallium, indium, thallium if you take. So top to bottom boiling points or decreases. So top to bottom boiling points or decreases. Boiling points or decreases. In this exceptionals are there that we'll discuss later. Then density increases. Density increases. These two you have to remember. Density and as well as boiling point straight away. Density and boiling points are straight away, that are so top to bottom decreases. These are then top to bottom increases the densities. Clear, my dear students? Yes. So now we'll discuss the next one, which are exceptions that we have to discuss here. So first, these two are noted, my dear students. Yes, look at. So first we have to discuss about the atomic size from top to bottom. Atomic size. Atomic size if you take, or atomic radius if you take, in the 13th group elements. So generally we can expect in the normal trends every group top to bottom atomic sizes are increases, right? But here in this one of the exception is there, so that we are discussing periodic trends which are present exceptions. So exceptions ఇందులో డిస్కస్ చేస్తా ఉన్నాం. First we are discussing about the atomic size, my dear. So atomic size generally we can discuss, that is top to bottom it is increases. So what we are expecting? So boron, then aluminum, then gallium, then indium, then thallium, right? So this we can expect. But actually what happens there? So gallium is less size when comparative to the aluminum. So this will come to there. So now correct order is correct order is boron, then after gallium, then after aluminum, then after indium, then after thallium, Clear? Understand all of you? So why? What is the reason gallium is less size when comparative to aluminum? The gallium is less size when compared to aluminum. So reason is, remember my dear students, reason is poor shielding effect of 3D electrons. Poor shielding effect of poor shielding effect of 3D electrons. What does it mean here? What does it mean? Sir, here, sir, it is gallium. Actually, the atomic number is 31, right? The before that, so 3D10, then the 4p1 electronic configuration. 3D10 is there. 3D10. So 3D10, what happens? 10 electrons are filled in only one cell. So once all the electrons, these are having the poor screening, the atom will be shrink like this. So what happens here? Just assume it. So this is the cell. In the third cell, what happens? In the third cell, 10 electrons are there. These are poor screening effect. Poor screening effect, nothing but these are attract more towards the nucleus. More attract towards the nucleus. Once more attract towards the nucleus, atoms shrink like this. So that is what size will be decreases. Clear, my dear students? So poor screening effect of gallium, then atomic sizes, it happens like this. Okay, understand? Next order, this is the first one, exception. So next you have to note it. So second one, that is electronegativity. Second one, what we have to discuss? Electronegativity. Electronegativity. So for electronegativity, sir, one shortcut trick I will tell to you. One shortcut trick. So electronegativity, boron is the top, right? Boron is the top. Then after, sir, you have to remember the electronegativity order with a shortcut trick. Trick for the electronegativity of 13th group elements, or see, look at big tiger, in garden always, Big tiger in garden always. Remember, my dear students, big tiger in garden always. Very, very important shortcut trick. See, B nothing but boron. It is a more electronegative. Then next tiger, thallium. Then next indium. Then next gallium. Then next aluminium. Sir, electronegativity for the boron is 2. Then this is 1.7. Sorry, 1.8. Then this is 1.7. This is 1.6. For aluminum is 1.5. These are the electronegativity values of these elements. So to remember this order, you have to remember big tiger in garden. Big tiger in garden always. Big tiger in the garden always. This is very important shortcut trick. Clear? Understand? We'll go for the next trick. So we'll go for the next trend. So second trend is electronegativity. First trend is atomic radius. Atomic size, what we have discussed here. So only the gallium atomic size is so less than aluminum. That only changes in the atomic radius. Next changes are what are present? Electronegativity. So what are the electronegativity changes are there? Look at. Then what are the changes of electronegativity? Look at. So to remember the shortcut trick, so big tiger in garden always. Clear? So next third one we are taking. Third one that is melting point. Melting point. Remember even the melting point. So when we are discussing about the boron, I told that boron is the hardest material. Then icosahedron structure is there. Black crystalline solid. It contains high melting point, I told. Even here also, when compared to all elements, boron has high melting point. So trick to remember the melting point order, my dear. Trick to remember the melting point order. So look at big apple tree. Big apple tree in garden. Big apple tree in garden. Previous what we are discussing. Big tiger in garden always. Big tiger in garden always. That is the trick for electronegativity. Now the second trick, that is big apple tree in garden. So what is the trick? So boron is the highest melting point. Then after aluminum, then after thallium, then after indium, then after gallium. The gallium is the least melting point, my dear students. Least melting point, that is 29 degrees Celsius. This is highest melting point. That is the least melting point. So 29 degrees Celsius will be there. So gallium, that's what it at room temperature itself it can be melt. Room temperature దగ్గర ఈవెన్ మన చేతిలో కూడా రబ్ చేస్తే గట్టిగా సో అది మెల్ట్ అయిపోతుంది. దట్ ఈస్ వి ఆర్ డిస్కసింగ్ హియర్. So what is that? Gallium is the least melting point at 29 degrees Celsius. Boron is the highest melting point. So note down the trick, all of you. Note down the trick. Yes, who's that? Chintu 7211. Do you know Lingam sir? Yes, I know Lingam sir. So TH campus, user campus, please see TH. Okay, clear, my dear students. So melting point, to remember the melting point, big apple tree in garden. To remember the order of electronegativity, big tiger in garden always. Big tiger in garden always. Then next ionization energy. So next, ionization energy. Ionization energy. To remember the ionization energy, what is the shortcut? To remember ionization energy. Ionization energy. Ionization energy. So you have to remember, so graph for this. So these are the ionization energies. These are the elements, trends of elements that are. So look at what will be there. So you have to remember like this. Yes. So you have to remember W, look like a W. So, but somewhat not exact W like this. So somewhat cross like this. You have to take the W. So here boron element. Then this indicates boron, aluminium, indicates gallium, then indicates gallium, indium, then indicates then thallium. Okay, so here and this, if you observe carefully, first boron to aluminium ionization energy decreases, again aluminium to gallium ionization energy increases. Why? Gallium ionization energy is greater than that of aluminium. The reason is the atomic sizes of gallium is less than that of aluminium, right? So due to the poor screening effect, the reason is due to poor screening or shielding. Poor shielding effect. Clear? Understand all of you? Right? Next one more. If you come, then gallium to indium. Generally ionic sizes, what is ionization energies or decreases. Then again indium to thallium ionization energy increases. So why thallium ionization energy is greater than that of indium? What is the reason? So here lanthanoid contraction. So thallium it contains due to lanthanoid contraction. They're asking a question again, lanthanoid. What is the lanthanoid contraction, sir? So lanthanoid contractions are, so thallium after the lanthanoid situation get, so before this cell that we can get the 4f14 electrons will be present. The 4f electrons. So again, due to the presence of poor screening effect, atom size will be shrink like this. So once atom size shrinks, once atom size decreases, ionization energy increases. Understand all of you, my dear students? So what are the four trends that we are discussing now? So once again, listen carefully. So for all the shortcut tricks in one frame that we'll discuss. So one is first one, atomic size, my dear student, right? Then next one, what we are discussed, melting point we are discussed, second one. Next, third one, what we are discussed, man? Third one, what we are discussed? So that is electronegativity we are discussed. Then fourth one, what we are discussed, man? So fourth one, ionization energy we are discussing, right? Yes. So atomic size, first one. So what is the trend? So boron after atomic size gallium, then after aluminum, then after indium, then after thallium. So the reason is gallium atomic size is less than that of the aluminum due to poor screening effect, poor shielding or poor screening effect. Both are same, man. Both are same. Poor screening effect also, the poor shielding effect and kuda anochu. Next, come to the melting point. So what I told for the shortcut trick for this, big tiger, big tiger in garden always. In garden always. In garden always. Always. In garden always. This is the trick. It's a big B. Boron. Then tiger, thallium. Thallium. Then in indium. Then gallium. Then aluminium, my dear students. Clear? Understand? So big tiger in garden always. Big tiger in garden always. Next, electronegativity. Look, my dear students, what about the electronegativity? Big apple tree. Big apple tree. Big apple tree. Then, sir, you have to remember the electronegativity. Sorry, this is electronegativity order. It is. So this is electronegativity order. Then this is what? Melting point order. So melting point order, how to remember? So big apple tree in garden, big apple tree in garden. So how to remember? So boron first, the most highest melting point, then after aluminium, then after thallium, then after indium, at last gallium. So gallium is the least melting point. I told how much melting point? 29 degrees Celsius is present. It is almost near to the room temperature. Then if you come to the ionization energy, what I told, you have to remember the graph like this. You have to remember the graph like this. Then, so in this case, then first boron you can get, then boron, aluminium, then gallium, then indium, then thallium. So order, how to note it? So order, first boron, then next what will be there? Next what will be there? Thallium. Next what will be there? Gallium. Next what will be there? Aluminium. So next what will be there? Indium. Clear? So boron highest, lowest ionization energy. Then after thallium have to take. Then after gallium have to take. Then after gallium, boron, thallium, gallium. Then after aluminium, least case which is indium. Okay. So note down in one frame all these. Boron, thallium, gallium, aluminium, indium. Yes, all the periodic trends we are done. So next we have to discuss about the reactivity towards air. Next we have to discuss about the reactivity towards air. So air present what man? Nitrogen as well as oxygen. So look at all of you. Reactivity towards air. So air is present oxygen and as well as nitrogen. So look, my dear students, the 13th group elements, whatever it is there. So what are the 13th group elements? Boron, aluminium, gallium, indium, thallium. So these are the oxidation states plus 3 I told, right? So in case when it is reaction with oxygen, so oxygen oxidation state -2, right? Then you can get, sir, E2O3 type of compounds. E2O3 type of oxides we can get. Clear? Next, in case, say element, 13th group element, oxidation state, what I told, +3. Then when it is treated with nitrogen oxidation state -3, then En type of nitrides we can get. So here look at boron actually do not react. It is a very hard material. The boron do not react when it is present in the crystalline form. Boron do not react react when it is present in crystalline form. Boron ఎయిర్ తో రియాక్ట్ అవ్వదు ఎప్పుడు క్రిస్టలైన్ ఫార్మేషన్ లో ఉన్నప్పుడు. క్రిస్టలైన్ ఫామ్ యాక్చువల్ గా సాలిడ్స్ టూ టైప్స్ గా ఉంటాయి, క్రిస్టలైన్ ఫార్మేషన్ అండ్ యాజ్ వెల్ యాజ్ అమార్ఫస్ ఫార్మేషన్, రైట్? Solids are in the two types, crystalline and amorphous. When it is present in the crystalline formation, do not react with air. Then what about the aluminum, man? So aluminum can react in case aluminum is there like this. So aluminum ఎయిర్ తో పైన ఉన్న లేయర్ తో రియాక్ట్ అవుతుంది. రియాక్ట్ అయిన వెంటనే Al2O3 అనే ఆక్సైడ్, థిన్ ఆక్సైడ్ లేయర్ ని ఫామ్ చేస్తుంది దాని చుట్టూ. ఎప్పుడు ఇది క్రిస్టలైన్ ఫార్మేషన్ లో ఉన్నప్పుడు. అంటే ఆక్సిజన్ రిమైనింగ్ ఎయిర్ ఏదైతే ఉందో, సో దాట్ ఇట్ వోంట్ ఎంటర్ ద ఇన్సైడ్ ఆఫ్ అల్యూమినియం. సో ఇట్ కెన్ ఫార్మ్ ఓన్లీ ద ఎబో లేయర్. సో ఆ ఎబో లేయర్ కూడా ఆక్సైడ్ ఫార్మేషన్ అయిన తర్వాత సో కెనాట్ రియాక్ట్ విత్ ఎయిర్. సో Al2O3 act as a protective layer for the further reaction. Clear, my dear students? Understand all of you, right? So aluminum can form a thin layer. Aluminum can form thin layer, that is protective layer, that is Al2O3 above surface of aluminum metal. But both can be react when it is present in the amorphous form. So remember, boron and aluminum can react. Boron and aluminum can reacts when present in amorphous form. Amorphous form లో ఉన్నప్పుడు సో ఇది రియాక్ట్ అవుతుంది amorphous solid గా ఉన్నప్పుడు. Remember, my dear students. So what type of oxides it can form? Look at what type of oxides it can form, that we'll discuss. Observe it carefully. So what type of oxides it can form? I told that E2O3 type of oxides it can be formed. E2O3 type of oxides it can be formed. E2O3 type. So E nothing but what I told: boron, aluminum, gallium, indium, thallium. Boron, aluminum, gallium, indium, thallium. So look at B2O3, then Al2O3, then Ga2O3, then In2O3, then Tl2O3 type of oxides it can be formed. So for all these elements of oxidation state is +3. Oxidation state is +3. Then from the here onwards, the gallium, it can also form Ga2O, then In2O, then Tl2O. Like that formations also forms. Here that is +1 oxidation state. Here these are +3 oxidation states. So ఇవి +3 ఆక్సిడేషన్ స్టేట్ ని ఫామ్ చేస్తాయి, ఇక్కడ +1 ఆక్సిడేషన్ స్టేట్ ని ఫామ్ చేస్తాయి. ఓకే మై డియర్ స్టూడెంట్స్, అండర్స్టాండ్ ఆల్ ఆఫ్ యూ, రైట్? వెరీ గుడ్. సో ఇది +1 ఆక్సిడేషన్ స్టేట్ ని ఫామ్ చేస్తుంది. ఓకే, దెన్ +3 ఆక్సిడేషన్ స్టెబిలిటీ టాప్ టు బాటమ్ డిక్రీజెస్. హియర్ +1 oxidation stability top to bottom increases. So remember, +3 oxidation state stability down the group decreases down the group. So here +1 oxidation state stability increases down the group. This is very important, my dear students. Only the reason is inert pair effect. Inert pair effect. So what is the inert pair effect? What is the inert pair effect? Inert pair effect, nothing but, so whatever the electronic configuration, if you take boron, aluminum, gallium, indium, thallium. So boron, in case if you take Ns2, Np1, general electronic configuration we have seen, right? So here the two electrons, what will be there? Two electrons. The two electrons are not involved when going down the group. These two electrons are not involved in the bond formation while going down the group. In the oxides or halides, oxides కానివ్వండి, halides కానివ్వండి, sir, ns2 electrons are not, they are not ready to involve in the bond formation. These two electrons are two electrons. Which are the two electrons, man? ns2 electrons are not ready to involve in bond formation. Yes, exactly, bond formation low involve. Okay, right? So understand? Yes. So that is the reason here +1 oxidation state, increases down the group. +3 oxidation state decreases down the group. Yes, note this. Then one of the point we'll discuss here. Yes, note down. Yes, we'll discuss next one. Yes. So here the oxidation states when we are discussing. Oxidation states of oxides when we are discussing. So from the gallium onwards, so Ga, gallium, when it is present in the +3 oxidation state, gallium +1 oxidation state if you take. So where the stability of both, the gallium is more stable. Then indium, in case if you take indium +3 oxidation state, then indium +1 oxidation state, In these, which is more stable, indium +3 is more stable. Then thallium, in case if you take thallium +3, then thallium +1 oxidation state. In these two, which is more stable? Thallium +1 is a more stable. Stability increases. +1 oxidation state. Stability increases. I told. Then here from here to there, +3 oxidation state. Stability decreases. Clear, my dear students? Next, when we are discussing about the oxides of all these, so boron is there, aluminum, then gallium, then indium, then thallium, right? So boron, it is non-metal. Boron is non-metal. Then aluminum, gallium, metalloids, indium and thallium, so metals, So remember, non-metal oxides are acidic in nature. Then metalloid oxides are amphoteric in nature. Then metal oxides are basic in nature. Remember, so that is what. So aluminum oxide Al2O3. Then amphoteric in nature. Amphoteric in nature. Then it can react with acids and as well as bases. Acids and as well as bases. Clear, my dear students? That is what we are calling it as amphoteric. Amphoteric meaning, so it is act as a acid as well as base. Even the gallium oxide also, it is amphoteric. It can react with acids as well as bases. So note this trend. Then we'll discuss about the yes. Next we have to discuss reaction with the halogens. So reactivity towards the halogens. So before going to reactivity towards halogens, reaction towards with acids and bases. Remember, boron do not react with acids or bases. Bases to kane, acids to kane react avadu when it is present in the crystalline formation, my dear students. When it is present in the crystalline formation. But aluminum, I told that, can react with acids and as well as bases. Acids to react avutundi, bases to react avutundi. Acids to react avutundi, bases to react avutundi. So look at, my dear students, look at that is which is aluminum. I told aluminum oxide. It can react with HCl. It can react with HCl to form AlCl3. So aluminum, only aluminum in case if you take, not even aluminum oxide also. Aluminum, if you take aluminum, it can react with acid, then can form aluminum trichloride, plus it can release hydrogen gas. Even remember, so aluminum can react with the sodium hydroxide, then NaAlO2, sodium metaaluminate, then plus hydrogen gas will be formed when it is reaction with a base. Then this further reaction with a NaOH, sir, Na2AlOH taken 4, sodium metaaluminate will be formed. So these are the reactions. So aluminum can react with the acids, then aluminum can react with the bases. So acid and base both can react, so that's what we are calling, it is amphoteric in nature. Amphoteric in nature. Understand, my dear students? Yes, note down that. Yes, next one, reactivity towards the halogens. Yes, reactivity towards the halogens. Halogens. What are the halogens, man? Then these are the halogens. Sir, element E, nothing but what? 13th group elements. So 13th group elements, when it is reaction with the halogens, then EX3 type of halides will be formed. So what are the EX3 type of halides? Sir, in case if you take in case chlorine, if you take BCl3, then AlCl3, then boron, aluminum, gallium, GaCl3, then InCl3, then thallium, TlCl3, like this will be formed. Then, so even here also, these all of oxidation state plus 3, oxidation state plus 3, plus 3 oxidation state, down the group decreases, right? Down the group decreases. Why reason decreases then? So due to the inert pair effect. Then in case if we take gallium Cl, then gallium, indium, then Cl, then thallium, Cl. So in these, when it is compared with the GaCl3 and GaCl2, which is greater stability, of course GaCl3 is greater stability. So iron, so indium trichloride, then indium, so monochloride. So which is trichloride is more stable. Then thallium trichloride and thallium monochloride, which is more stable? Thallium. So monochloride is the most stable. Understand all of you? Yes. So next, so we have to discuss about the reducing agent property and oxidizing agent property. So note down this. Next, compare reducing power. Next, compare oxidizing power. Compare reducing power and compare oxidizing power. Compare reducing power. So then after oxidizing power, both will discuss. So when gallium, if you take, so GaCl3, then GaCl, if you take. So Ga plus 3, then Ga, both if you take. So Ga plus 3, then Ga plus 1 if you take. Which is more stable? Of course, Ga plus 3 is the more stable. Ga plus 3 is the more stable. This is stability. Stability. Yes, clear. Stability order is that. Okay. Now, if you take Ga plus 1, for the stability, remember my dear student, for the stability, it lost 2 electrons. So look at Ga, then plus 3 plus 2 electrons. So a element or ion, when it is lost electrons, that we call oxidation. Any substance which is oxidation takes place, that is reducing agent. A substance which oxidation takes place, that act as reducing agent. Clear, my dear students? Yes. So that you have to remember, so that GaCl is act as better reducing agent than GaCl3. Clear? Understand? So GaCl, why it is a better reducing agent? It can last 2 electrons. It can last 2 electrons. So that is the reason it is a better reducing agent. So now if you compare the oxidizing power, note down this, please, note down. Yes, compare oxidizing power. Compare oxidizing power. Yes, oxidizing power. Yes, before going to the oxidizing power, look at thallium, thallium plus 3, then thallium plus 1. Which is more stable? Which is more stable? No doubt thallium is a more stable. Stability order. Stability. Clear, my dear students? So that is what here, thallium plus 3. By gaining of 2 electrons, it is ready to convert Tl plus 1. Tl plus 3 స్టెబిలిటీ కోసం 2 ఎలక్ట్రాన్స్ తీసుకొని Tl plus 1 గా కన్వర్ట్ అవుతుంది because it's more stable. So what happens in the reaction? Reduction is happens. The gain of electrons we call reduction. Gain of electrons we call reduction. Yes, reduction is happens. So in the reduction, if you observe, the substance, which reduction takes place? Which reduction takes place? Act as oxidizing agent. Oxidizing agent. Clear, my dear students? That is what? So TlCl3 act as better oxidizing agent. Better oxidizing agent than TlCl. TlCl. Okay, clear? Understand all of you? Yes. Let's note down the comparison of both. Note down the comparison of both. Here one of the previous year question that we'll discuss. Here one of the previous year question that we'll discuss. So look at, my dear student. So taking the stability of taking a stability factor, taking a stability factor, which one of the following represent? Which one of the following? Which one of the following? Which one of the following represent correct relationship? Represent correct relationship. That is the question actually. So look at, so orders are given. That is, A is mentioned. TLI is greater than TLCl3. TLI3. Then B is mentioned. TLCl3 is greater than TLCl. Then C. Then I3 is greater than INI. The next fourth one, D, that is ALCl is greater than, say, ALCl3. So actually the options are like this will be there. So A and B, then B, so B, then C and D, then C, so A and D, then D, so B and D, like this will be there. B and D, like this will be there. So look at here, which are correct. So TL plus 1 is plus 3. Plus 1 plus 3 oxidation state, if you observe the stability order, which is correct. The plus 1 is more stable. Plus 1 is more stable when comparative to plus 3, right? Then if you come to there, TLCl3, TLI3. So here you have to remember from the gallium, indium, thallium. So plus 3 plus 3 plus 3 stability, what happens? Decreases. So plus 3 is more stable. They are mentioned, it is wrong. It is wrong. Then the C option, indium plus 3. So indium plus 3 is more stable, right? So indium plus 3 is more stable when comparative to indium plus 1. So this is more stable, both. This is less stable. So this is correct. A and C are correct. Then next one, that is AlCl3, AlCl, AlCl3. So this is wrong. Then which are correct? So A and C are correct. So actually this is C. A and C is correct answer. So C option is correct answer. Okay. So this is one of the previous year question. So note it, my dear student. Note it, all of you. Yes, look at all of you. So next we have to discuss about some important compounds of boron. So one is borax, then one more boric acid. Borax and boric acid. So first one we are discussing, that is borax. Borax. The borax formula is Na2B4O7 10H2O. This is borax formula. Borax formula. So in the galleries, borax contains Na2B4O7. Look at Na2B4O7, 5H2O it contains. Na2B4O7, 5H2O. Then glass borax. Borax contains only Na2B4O7 without hydrated water molecules. So actual formula of borax is then Na2B4O5, Na2B4O5, OH taken 4. Look at, observe it carefully. This is very important question. Sir, Na2B4O5, OH taken 4, then dot 8H2O. This is the original formula actually. So actually the structure of this Na2B4O5, OH taken 4, how it will be present, the boron, then the boron, then boron atoms are there. Sir, in between them, bridged oxygen atoms, then bridged oxygen atoms are there. Then here, so look at, for this boron, here OH is attached. Then even in this case also OH is attached. Of course, one more bridged oxygen atom like this. Then here OH is attached. Then OH is attached. So remember, listen, my dear students, very important points are there in it. So this is a original structure. Wherever the 4 bonds are there, surrounded by the boron. 1, 2, 3, 4 bonds are there. So actually, boron valency is 3, right? Wherever the 4 bonds are there, it can get negative. Wherever the negative charge is there, to satisfy the negative charge, Na plus we can get. Na plus it will be satisfied. So wherever the negative charge is there, Na plus will be there. So entire structure it contains Na2, yes, 2 Nas, then B4, then O5, 1, 2, 3, 4, 5, O5, OH 1, 2, 3, 4, OH taken 4. Clear? So dot 8H2O, it is water, hydrated crystal we call, hydrated crystal. So here they are asking a question, how many BOB bridge bonds are present? How many BOB bonds? So look at 1, then 2, then 3, then 4, then 5. So 5 boron, oxygen, boron bonds are present. 5 boron, oxygen, boron bonds are present. Then next one, look at. So next one, that is boron in this case, boron atom in this case. These two boron atoms are sp3 hybridized. Then remaining these two boron atoms are sp2 hybridized, sp2, sp3. So sp2 and sp3 hybridized boron atoms are present. Hybridized boron atoms are present. Clear? Understand, my dear students? So this about the borax still will be there. Note down the structure first, then we'll discuss next one. Yes, next, so look at all of you. Then some of the chemical properties of borax in case if you take. Borax chemical properties. So what is the borax formula? Na2, B4, O7, 10H2O, I told you. So first in this case, if it is addition of water, what happens? The aqueous solution of borax is basic in nature. Aqueous solution of borax basic in nature. Remember, they will ask a question, aqueous solution of borax nature is acidic, basic, neutral, like that they will ask. Then basic in nature. Why basic in nature? Sir, Na2B4O7, without hydrated water molecules, when it is treated with the water, H2O to reaction cheste. Then, sir, 7H2O water molecules to reaction cheste. Then you can get the 2 moles of NaOH plus, then H3BO3. So borons, how many are there? 4. H3BO3, like this will be formed. So this is a weak acid, weak monobasic acid. Monobasic acid. Why we are calling monobasic acid? That also we'll discuss. Look at weak monobasic acid, but this is strong base. That is what we are calling it is basic solution. Andukosam dinni basic in nature antam. Okay, my dear students. Then you can observe one more thing here. What is that? Here weak acid is there. Strong base is there. Then plus weak monobasic acid. It is monobasic acid, weak acid, strong base. If rendu add cheyadam dwara ee salt form ayindi. The salt of this is we call salt of strong base and weak acid. So that is what it is act as a buffer. So which buffer it is? The buffer of salt of weak acid and strong base. So it is the buffer of the buffer which is acidic buffer. Acidic buffer we call. What we call acidic buffer. It is act as an acidic buffer. Weak acid and strong base. The mixture of weak acid and strong base. The mixture of weak acid and salt of strong base. The mixture of weak acid and salt of strong base. We call it is acidic buffer. Clear all of you? Understand, my dear students? Then heating effect of borax we have to discuss. Heating effect of borax have to discuss. Heating effect of borax have to discuss. Sir, Na2B4O7, then 10H2O, when it is treated with the heating, when it is heating, then by the loss of heating, by the loss of H2O, 10 H2O molecules completely, 10 H2O molecules, we can get Na2B4O7. Na2B4O7, unhydrated borax we can get. Na2B4O7. So unhydrated, anhydrous we call. Anhydrous, yes. On further heating, so malli heat cheste, on further heating, so you can get NaBO2, sodium metaborate, sodium metaborate. Then, and also we call it as B2O3, and also forms B2O3. Then this both the mixture we call glass bead. So this B2O3, it is used in borax bead test. Borax bead test. So in the borax bead test, if you see, so for example, so B2O3, when it is treated with cobalt oxide, it gives blue color. So for the identification of colors of metal oxides, so then based on the colors we can identify the metal oxides. So that is we call borax bead test. It is used in the borax bead test also. Clear? Understand, my dear students? So next we have to discuss one more important compound, that is H3BO3, orthoboric acid. H3BO3. It is, I told that, weak mono basic acid. Why we call it as a weak mono basic acid? So actually, say H3BO3, we can also write BOH taken thrice. Then BOH taken thrice, when it is treated with H2O to treat cheste, then BOH taken 4 minus, then plus H plus will be formed. So by the addition of water lo add చేసినప్పుడు ఏ సబ్స్టెన్స్ అయితే H plus రిలీజ్ చేస్తుందో, how many H plus it releases? Only one H plus it releases. So only one we call it as mono. Sir, where the H plus are releases, that we call the basic acid. Basicity is 1. So n factor for this is 1. So this is what we call the monobasic acid. This is what we call monobasic acid. Understand, all of you? Right? Yes. So note down this. Okay, students, we'll discuss the remaining topic tomorrow. Okay, thank you very much.